Okay, hello, Megan. Basically, we're here today as part of the Science Week, and we're actually at the new Norcia Deep Space Station radio telescope, which you can see behind us. How are you connected to all this?
Well, I'm an astronomer from the International Centre for Radio Astronomy Research based in Perth, so I work for Curtin University. And while I'm employed as a researcher, I do quite a bit of outreach, and the project that we're running here today is to do with National Science Week, and it's basically to take astronomy out to the public and show people that astronomy doesn't have to be just optical, it doesn't have to be just visual. So we have a couple of optical telescopes that we can look at the sun with. They've got big filters on the front to make them safe to look at the sun. We've also got a dipole from a telescope called the Murchison Wide Field Array, which is a prototype telescope for the square kilometre array. That's tuned to, at the moment it's listening to a radio station to demonstrate the fact that, you know, if you put telescopes like this in the city, what you pick up is interference, stuff that you're not interested in, stuff that coming from the sky is too faint to be heard over the background noise level in a city. And we've also got a small satellite dish as well, which is used to pick up radio transmissions from the sun.
Okay, and what's the idea of the radio transmissions from the sun aspect? Why?
Well, the sun is a broadband source, so everything in the universe that's warm emits over the whole electromagnetic spectrum, so right through from gamma rays at the high energy end through to radio waves at the low energy end. So the sun transmits most of its emission in the optical, which is the stuff that we can see that your eye is sensitive to, but it also emits infrared radiation, which is the stuff that makes you feel warm. It emits ultraviolet light, which is the stuff that gives you sunburn. It also emits radio waves, so it emits over the whole spectrum. And by looking at different parts of the spectrum, you can actually tell different physics about what's going on in the sky. So astronomers are basically physicists, and we use all different parts of the spectrum to try and understand what's going on in the universe. And the more different bits of the spectrum you look at, the better you can understand the physics of what's actually happening. So radio is just one way that we can do that.
Right. So do humans emit radio transmission, or a little bit less than that?
They will, but at a very, very, very low level. It would be incredibly hard to pick it up, I suspect. Right. So humans, body temperature, your core is about 37 degrees Celsius, so you emit most of your radiation in the infrared part of the spectrum. So if you look with an infrared camera at somebody, you can see which bits of them are hottest and which bits are coldest.
Right. Well, I guess you don't want to get too many people together just in case it builds up. Okay, and how are the public actually taken to radio astronomy, the stuff that they can't see?
Well, it's been interesting seeing people's reactions, actually. So we've had, one of the things about doing this kind of outreach in Western Australia is that most people have heard of the square kilometre array, which I think is fantastic. Somebody somewhere has done a fantastic job of getting this into the public consciousness. So people are aware that there is a big telescope and that it's not optical. But the thing with radio astronomy is that most people assume that because they associate radio with things like Triple J or ABC National Radio or whatever, they think that astronomers sit there with headphones on like Jodie Foster in Contact and listen for signals. Right. So that's what everybody assumes, that they're going to be listening to a signal. So what we've done with the radio telescope is that, yes, we've got a speaker there to show you what the sound sounds like, but it just sounds like white noise. I make the point that if you just sit and listen to that all day, one, you wouldn't get very much information out of it, but two, it would drive you completely nuts. Right. So we take the sound output from that and run it through a computer, so you get a visual representation of the signal, which is much closer to what we do as radio astronomers. We take observations from telescopes and we run them through computers to make images and to look at spectra and things like that.
Okay, so what do the guys at SETI do, the Search for Extraterrestrial Life, do compared to, say, the Square Kilometre Array guys?
Well, SETI is actually one of the science goals of the Square Kilometre Array. So there are 5 main science goals for the Square Kilometre Array, and one of those is looking for extraterrestrial intelligence. A lot of the SETI work that's currently done involves using existing telescopes and basically piggybacking. So they look at the sky and they look at whatever astronomers are interested in. But the signals are also processed through a specific receiver for SETI, which then gets sent to people around the world for something like SETI at home, so anybody anywhere can download the screensaver and run the data processing on their computer and look for signals from aliens.
Right. And do we actually know what an intelligent signal looks like?
Well,
Triple J, I guess. But.
Triple J, yeah. We've got some idea based on the signals that we generate. But whether we'll actually ever detect any is another matter. But if we don't look, then the probability of us finding any is 0, because if you're not looking, you're not going to find anything at all.
Absolutely. So basically, we're counting down now, I guess, to the Square Kilometre Array sort of final decision, I guess.
Yes, the final decision as to which site it's going to be built on is going to be made in 2012. So it's either going to be here in Australia, so the bid is Australia and New Zealand combined, or in Southern Africa, so based in South Africa but with stations in other countries in Southern Africa as well.
And what will your part be in that, whether it's South Africa or Australia?
I don't know. Well, I'm looking forward to the data that comes from it, but it won't be completed until about 2020. That's the goal for completion of the actual telescope and full science operations. So obviously that's a fair way in the future at the moment, but hopefully I'll still be in astronomy and hopefully get to play with some of the data.
I hope so. And What other projects are you working on or hope to work on?
Well, my particular field of research, I study starburst galaxies. So basically, big galaxies like the Milky Way out there in the universe, if they get close to each other, they will actually crash into each other and merge. So I study those mergers and collisions. And what happens in those collisions is you get galaxies that basically, because you've got lots of stars, they're actually quite far apart. They sort of pass through each other and they sort of mesh, and eventually they oscillate and they eventually merge. But the gas clouds do actually hit and it sends shockwaves through the gas clouds, and that shockwave can actually start a collapse forming. And when the collapse starts, that's when you get stars being created. So I study star formation in galaxies crashing into each other.
Wonderful. I think there's a butterfly galaxy. Is that one of them, where you had two merging galaxies going through to each other, and then you get a nice couple of swirls?
Yeah, you get these big tails of stars that spread out from them. Yeah, that's right.
So I guess obviously the gas colours change colour, and then you know, something's happening there.
Yeah, well, you can, again, with optical images, you see a lot of images from Hubble which are actually false colour. So what they do is they look through various different filters, and you can take, so the oxygen, you colour it green, you see the hydrogen, you colour it red, and you might see nitrogen, colour it blue, and then you put those three images together, and you get a fantastic image that doesn't look anything like what you'd see through a telescope with your eye, but tells you a lot about the physics going on inside the galaxy. And we do exactly the same with radio telescopes. So we might look at 1.4 gigahertz, 8 gigahertz and 30 gigahertz and combine the images in the same way, so colour one red, one green and one blue, and make a colour image. And again, that tells you something about the physics.
Okay, and what about the 21 centimetre line? Does that come into it at all?
Yeah, the 21 centimetre line is 1.4 gigahertz. That's a really important line in radio astronomy because it's where the hydrogen atom emits a lot of radiation. So hydrogen makes up 3/4 of the stuff in the universe that we can see, so it's quite important to know where it is and how fast it's moving. So we can map galaxies, we can map rotation speeds of the spiral arms using it. But it's a very, very low probability line. So it's basically, you've got, in a hydrogen atom, you've got a proton and an electron, and each of those has a property called spin, and the spins can either be aligned or opposite.
Up or down?
Yes. And what happens is when that flips, that's when you get the 21 centimetre line being emitted. There's a radiation emitted in that transition. But because there's such a low probability of that transition actually occurring, in normal hydrogen in a lab on the Earth and in the Sun, you won't see it because the atoms will actually hit each other first and de-excite that way before they have a chance to actually flip. So you only see it in tenuous gas out in the spiral arms of galaxies.
Right. And what about